Hello everyone, welcome back to the class. Today we are going to discuss a very important chapter that is electromagnetic induction. This is the greatest discovery in the field of physics. So what is the meaning of this electromagnetic induction and how the things carried forward with Faraday's laws of electromagnetic induction and all. We'll see that. This is the first lecture. I welcome all of you. Look at this. There is one word called magnetic flux. The name of the word is magnetic flux. Okay. So you must have heard about flux, no? Electric flux. In the first chapter, you must have heard about electric flux. Here we are going to study about magnetic flux. The symbol is going to be phi b. We can write it just phi also. Whatever this phi e is there, no? So we use this phi e for electric flux. Yes, everybody knows that, because flux means symbol is pi only, and pi b means we use it for magnetic flux, right? So pi e and pi b. So pi means this flux only, but e means electric and b means magnetic. All right. Dear children, look at this. There is one simple definition for this magnetic flux. Very simple it is. What is the definition of magnetic flux? Magnetic flux definition is, it's very simple. The number of magnetic field lines, the number of magnetic field lines, magnetic field lines passing, magnetic field lines passing perpendicular to the surface, perpendicular to the surface is called magnetic flux. It's quite simple. Okay, just like electric flux. What was electric flux? That was the number of electric field lines passing perpendicular to the surface, right? So similarly, magnetic flux means it is number of magnetic field lines passing perpendicular to the surface, right? Now you must be wondering, what is this perpendicular thing and all. Look at this. For example, I have got one surface here. Here there is one surface like this. You understand the meaning of a surface, no? Now it becomes difficult for me to tell you without coming into the picture and all. See, look at this. Through this surface, if some field lines, for example, there is some magnetic field which is going like this. Okay. Now, in this, how many field lines are passing? Three field lines are passing. That is only magnetic flux. That's it. That is a magnetic flux. So not two, three, right? How many are passing now? One, two, three, right? So three magnetic field lines are passing. That's why magnetic flux is three. That's it. That is the meaning of magnetic flux, right? See, this surface is there now. Whatever surface is given, through this surface, how many field lines are going? One, two, three. You can see them, right? For example, I have one line here which is passing through the surface. This is the second line, and this is the third magnetic field line passing, right? So all these three are passing. So that's why this is known as magnetic flux. I hope you got it. All right. Now coming to the next things, let us try to make a formula for this and to explain you how this surface looks like. A little bit I may come into the video also and explain you how that flux will. You understood that, things will become clear to you. Look at me. I think you can see me now. Now this mobile is there. No, for example, this mobile phone. So this is a surface now. Can you look at this? If I place my hand like this is a surface. Through this, look at this. For example, my five fingers are there. So if my five fingers are there, for example, thumb is going above. Now these four fingers are passing through this hand means magnetic flux is 4 at that. Are you understanding? So this mobile phone, for example, this pen is only one line is passing and other line is above and other line is below. So if only one line is passing through this mobile, through this surface, look at this surface, through this surface it should pass through. Then only it is known as magnetic flux. Already I have explained in electric flux also. You can watch those videos also. So magnetic flux means, perpendicularly it should go. This surface is there, no? Area is there, area vector, you know how the area vector will be. It will be along that. In that direction. So magnetic field lines are passing means it should be perpendicular. The angle between this surface and this line should be 90 degrees. So that is called as magnetic. I hope it is clear, whatever I have explained.
Yes.
Yes, okay. So that is known as magnetic flux. That's what I have given you here. Let us try to make some formula for this magnetic flux. Now, let us see how the formula can be made. Now, look at this, dear children. For example, I have taken this surface here. No? I have taken surface here, and here some magnetic field is passing like this. Okay. So magnetic field. What is the flux here? I mean, in this case, what is the flux? Tell me. Two is the flux, no?
Yes.
Okay. Now what I did, I took the same thing, same area is there, no? So same, everything is same, exactly same I have made here. Okay, I mean it is the same one. So whatever, I mean that container was there, I mean that area was there, no? That plate or whatever you want to call it a surface. Same thing I made here, but I increased the magnetic field. Now magnetic field has increased me. Don't you think magnetic field lines will also increase like magnetic field lines also increase, no? Yes or no? So here the magnetic flux is 2. How about the magnetic flux here? Look at this. How many are passing? One is passing. One line is passing here. Yes.
Four.
One line is passing. Another is passing. Three is four. Four lines are passing. No. Please turn off your mic. Yeah. Please turn off your mic. So here magnetic flux is 4, but area is same. No. So what was this area? This area was also A, and even this area is also same. But due to this magnetic field, so whatever this magnetic field has increased, no. So magnetic field has increased, and due to that magnetic field lines also increased. Due to that, flux is increasing. Don't you feel magnetic flux is directly proportional to magnetic field? If you increase the magnetic field, magnetic flux will increase, no? Okay. Then keeping those things, I mean that is like first one. First one we got magnetic flux is directly proportional to this magnetic field. Now here same magnetic field is there. For example, I have got this four magnetic field lines here like this. Okay, and the same magnetic field. So whatever these are there, no. So same magnetic field if you take here also. For example, I have taken the same magnetic field lines here also. So whatever magnetic field lines are there, I have taken them there also. And in this, what I will do, I will take one. I mean, I will place one small area here. I will place one small area here. So now, I mean, if I place one small area here, what is the flux through this small area? One is the flux here, no? Magnetic flux is going to be one. So here, I mean, magnetic field is constant, okay? Here, whatever magnetic field here and here, whatever it is, their magnetic field. So everywhere the magnetic field is same. So here it is constant. But here area is changing. Now, if you place another big area like this, now what is the magnetic flux here and there? Tell me. Here the magnetic flux is 1, and here the magnetic flux is 1, 2, and 3, right? So by increasing the area, also magnetic flux can be changed. Can I say magnetic flux is directly proportional to area? This is the second one. No? Can I say like that? Definitely, I can say that I have shown you. Yes, and all these should be passing perpendicular. Okay, this is very important. Perpendicular, it is very important. And here also, whatever field lines are, they should be perpendicular to the surface. So that is like we got second one. So then you must be thinking like pi b is proportional to ba, right? So you must be thinking pi b is proportional to ba. So this is the formula. And there is one more concept. No, actually, this is not the final formula. Not only this thing, there is will be some angle factor also. For example, now this, I mean, area is like this, but whatever this magnetic field is there, no, that, I mean, this is the area vector and all, you know, how the area vector will be. Area vector will be along this, no? And here, if you're keeping like this, area vector will be along this only. This is the area vector. And here it is along the area vector. Just now, when I came into the video, I was showing mobile and no, so it is the area vector. Here also area vector. So I was showing all these things to you. Okay, how this area looks, that surface mobile I was holding and hand I was holding, and through that hand the pen was entering, right? So area vector is like this. Now here also area vector is like this. Now if magnetic field lines are passing like this, look at this. Now there is some angle between this b and a, right? Here is theta, right? Now, what happens here? You have to take the magnetic field lines perpendicular to the surface, right? So whatever this B is there, no, don't you think this B can be split into two components? One is along the x-axis and one is along the y-axis. So along the x-axis, whatever it is there, so it becomes BA cos theta. It becomes BA cos theta, and next one becomes, not BA. It just becomes B cos theta, no? This red colored horizontal line B cos theta, and this one becomes B sin theta. Yes or no? With changing of angle, it will be changing, no? So that's why now don't you think only B cos theta is perpendicular to the surface? How about this B sin theta? B sin theta is just, passing over the surface, touching the surface. It is not going through the surface. It is just touching the surface. When I come into the video, I'll explain you. So B cos theta has to be considered or not. So what will be the magnetic flux there? So if you consider the magnetic flux, so that is like, what is the magnetic field perpendicular to the surface? That is like B cos theta. And afterward, what is that area? It is A. So you have to multiply B cos theta and A. You should ignore this B sin theta, because it is B sin theta is neither perpendicular or nor it is passing through the surface, right? You have to ignore this and you have to consider B cos theta. B cos theta and A you have to multiply. So once you multiply that, you are going to get the formula BA cos theta. Is it clear? Now, you must be having some doubt regarding this B sin theta and B cos theta. So let me explain those things also. I'll be explaining those things because that has to be made clear. Already in electric flux, I have explained that. But up to what level you have, and you must have understood that. Okay, can you see me now, all of you? Look at this. This is a mobile phone, okay? So how is the area vector? Everybody knows area vector is going like this, right? Area vector is like this. It is going. Now, if magnetic field line, it's fine. It is directly at this angle here, perpendicular angle is there. Now, if magnetic field line is going like this, means look at this. Magnetic field has come outside, no? It is passing like this through the surface. It has entered the mobile phone and it is coming here. Correct? Now, this magnetic field is there, no? It is making some angle with this A, right? Here is the A. Here is a vector A. This is the area vector like this. And here is the magnetic field. Now, between A and B, there is some angle, right? So now this B can be split into B cos theta and another is like B sin theta. Look at this. This is B, right? This is how B is. And this is B cos theta and this is B sin theta. B sin theta is just touching the mobile surface and it is going just like a butter on the bread. Jam ತರ ಬಟರ್ ತರ ಹಿಂಗ್ ಹಚ್ಕೊಂಡು ಹೋಗ್ತಾ ಇದೆ, ಪಾಸ್ ಆಗಿ ಹೋಗ್ತಾ ಇಲ್ಲ. ಬಿ ಸೈನ್ ಥೀಟಾ ಯಾವ್ದು ಹೋಗ್ತಾ ಇದೆ ಇದರಿಂದ ಪಾಸ್ ಆಗಿ, ನೋಡಿ ಇಲ್ಲಿ ಬಿ ಕಾಸ್ ಥೀಟಾ ಇದರಿಂದ ಪಾಸ್ ಆಗಿ ಹೊರಗಡೆ ಬರ್ತಾ ಇದೆ ತಾನೆ. ಸೊ ಅದಕ್ಕೋಸ್ಕರ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಪಾಸ್ ಆಗಿ ಬರ್ತಾ ಇದೆ ಅಂದ್ರೆ ಯಾವ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ತಗೋಬೇಕು ನಾನು? ಬಿ ಕಾಸ್ ಥೀಟಾ ತಗೋಬೇಕಾ ಅಥವಾ ಬಿ ಸೈನ್ ಥೀಟಾ ತಗೋಬೇಕಾ ಹೇಳಿ ನೋಡೋಣ. ಬಿ ಕಾಸ್ ಥೀಟಾ ತಗೋಬೇಕು ತಾನೆ. ಏರಿಯಾ ವೆಕ್ಟರ್ ಹಿಂಗಿದೆ, ಅದ್ರ ಜೊತೆಗೆ ಬಿ ಕಾಸ್ ಥೀಟಾ ಇದೆ. ಸೊ ಅದ್ರ ಸಲುವಾಗಿ ಬಿ ಕಾಸ್ ಥೀಟಾ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಹೋಗೋದ್ರಿಂದ ಬಿ ಕಾಸ್ ಥೀಟಾ ಇಂಟು ಎ ತಗೋಬೇಕು ತಾನೆ ನಾನು. ಎವ್ರಿಬಡಿ ಇಸ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್ ವಾಟ್ ಎವರ್ ಐ ಆಮ್ ಸೇಯಿಂಗ್?
Yes, sir.
Yes, sir.
Yes, I hope everybody got it. So ಅದಕ್ಕೋಸ್ಕರ ನಾನು ಏನ್ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದ್ರೆ, ಸೊ ಇಲ್ಲಿ ಏನ್ ತಗೊಳ್ಬೇಕಂದ್ರೆ ನಾನು, see the screen now?
Yes, sir.
Okay. See what I was saying, no? So whatever this, I'm sorry, really sorry for that. So component
No, sir,
of magnetic field, ಈಗ ಕಾಣ್ತಾ ಇದೆಯಾ? ಕಾಣ್ಬೇಕು ನೋಡಿ ಈಗ ಸ್ಕ್ರೀನ್.
ಇಲ್ರಿ ಸರ್, ನಮಗ್ ಕಾಣತ್ರಿ.
ಈಗ ಕಾಣ್ತಾ ಇರ್ಬೇಕು ನೋಡಿ. ಈಗ ಕಾಣ್ತಾ ಇದೆಯಾ ನೋಡಿ, ಚೆಕ್ ಮಾಡಿ. ಕಾಣ್ತಾ ಇದೆಯಾ? ಇಲ್ಲ, ಯಾರು ಕಾಣ್ತಾ ಇಲ್ಲ ಅವರು ಮೀಟಿಂಗ್ ಅನ್ನ ಬಿಟ್ಟು ವಾಪಸ್ ಬನ್ನಿ. ಲೀವ್ ದ ಕ್ಲಾಸ್ ಅಂಡ್ ಕಮ್ ಬ್ಯಾಕ್ ಅಗೇನ್ ಸೊ ದಟ್ ಇಟ್ ಇಸ್ ವಿಸಿಬಲ್. ಕಾಣ್ತಾ ಇದೆಯಲ್ಲ ಎಲ್ರಿಗೂ? ಕಾಣ್ತಾ ಇದ್ರೆ ಎಸ್ ಅನ್ನಿ. ಸ್ಕ್ರೀನ್ ಕಾಣ್ತಾ ಇದ್ರೆ
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
ಯಾರು ಕಾಣ್ತಾ ಇಲ್ಲ ಅವ್ರ ಎಸ್ ಅನ್ನಿ. ಯಾರು ಕಾಣ್ತಾ ಇಲ್ಲ ಅವ್ರ ಎಸ್ ಅನ್ನಿ. ಓಕೆ, ಫೈನ್. ಸೊ ನಾನೇನ್ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದ್ರೆ, ಇಲ್ಲೇನು ಬಿ ಕಾಸ್ ಥೀಟಾ ಆದ್ರೂ ತಗೋಬಹುದು, ಬಿ ಸೈನ್ ಥೀಟಾ ಆದ್ರೂ ತಗೋಬಹುದು, ನಿಮ್ ಇಷ್ಟ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಇನ್ ಕೇಸ್ ಏನಾದ್ರು ಈ ರೀತಿಯಾಗಿ ಸಿಚುವೇಶನ್ ಇದೆ ಅನ್ಕೊಳ್ಳಿ. ಈಗೇನಾದ್ರು ಒಂದು ಸರ್ಫೇಸ್ ಈ ರೀತಿಯಾಗಿದೆ. ಸೊ ಇದರಲ್ಲಿ ಏರಿಯಾ ವೆಕ್ಟರ್ ಅಂದ್ರೂ ಇದೇ ರೀತಿಯಾಗಿರುತ್ತೆ ಇದರದ್ದು. ಹೌದಾ? ಹೇಳಿದ್ದೀನಿ ಆಲ್ರೆಡಿ. ಈ ರೀತಿಯ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇಲ್ಲಿ ತಗೊಂಡ್ಬಿಟ್ಟು ಇದು ಬಿ ಇದೆ ಅಂದ್ರೆ, ಸೊ ಈ ರೀತಿಯಾಗಿ ಇಲ್ಲಿ ಲೈನ್ ಎಳೆದಾಗ ಈ ಆಂಗಲ್ ಇದೆಯಲ್ಲ, ಈ ಆಂಗಲ್ ಏನಾದ್ರು ಥೀಟಾ ಇದ್ರೆ ಇಲ್ಲಿ ಕೆಳಗಡೆ ಏನಾಗುತ್ತೆ? ಬಿ ಕಾಸ್ ಥೀಟಾ ಆಗುತ್ತೆ. ಈ ಕಡೆ ಇರೋದು ಬಿ ಸೈನ್ ಥೀಟಾ ಆಗುತ್ತೆ ತಾನೆ. ಆಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಏನಾಗುತ್ತೆ ಹೇಳಿ ನೋಡೋಣ. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಬಿ ಸೈನ್ ಥೀಟಾ ಇಂಟು ಎ ಆಗುತ್ತೋ ಆಗಂಗಿಲ್ಲ? ಅಂದ್ರೆ ಏರಿಯಾ ವೆಕ್ಟರ್ ಜೊತೆಗೆ ಯಾವ್ದಿದೆ ಅದನ್ನ ತಗೋಬೇಕು ನಾನು. ಏರಿಯಾ ವೆಕ್ಟರ್ ಜೊತೆಗೆ ಇರುತ್ತಲ್ಲ ಆ ಕಾಂಪೊನೆಂಟ್ ಅನ್ನ ತಗೋಬೇಕು. ಅಥವಾ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಟು ಸರ್ಫೇಸ್, ನೋಡಿ ಇದು ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಕೂಡ ಇದೆ ಮತ್ತೆ ಏರಿಯಾ ವೆಕ್ಟರ್ ಜೊತೆಗೂ ಇದೆ. ಸೊ ಅದಕ್ಕೋಸ್ಕರ ನಾನು ಬಿ ಸೈನ್ ಥೀಟಾ ತಗೊಂತೀನಿ. ಹೌದಾ? ಸೊ ಅದಕ್ಕೆ ಬಿ ಸೈನ್ ಥೀಟಾ ಇಂಟು ಎ ಆಗುತ್ತೆ. ಬಟ್ ಯೂಶಲಿ ನಾವು ಏರಿಯಾ ವೆಕ್ಟರ್ ಇದು ಏರಿಯಾ ವೆಕ್ಟರ್ ಮತ್ತೆ ಬಿ ನಡುವೆ ಇರುವಂತ ಆಂಗಲ್ ತಗೋದ್ರಿಂದ ಅದು ಬಿ ಕಾಸ್ ಥೀಟಾ ಆಗುತ್ತೆ. ಗೊತ್ತಾಯ್ತಾ ಏನ್ ಹೇಳಿದೀನಿ ಅಂತ ಹೇಳಿ? Did you understand
Yes,
all
sir.
this? Okay. So anyway, we got the formula. That formula is like magnetic flux formula is equal to phi b is equal to ba cos theta. I think you must have understood this. I mean, if somebody asks you what is magnetic flux means you should be able to tell the number of magnetic field lines passing perpendicular to the surface is called magnetic flux. Then this is for explanation, and this is the final formula. I mean, whatever I have written here, this is the final formula. That is phi b is equal to ba cos theta. Clear, dear children? Is it clear?
Yes.
Okay, fine then. Moving forward, look at the other things now. Maybe, I mean, this can be sin theta also. Now, what is the unit of magnetic flux? Unit of magnetic flux, look at this. And here this B means, what is this? Tesla. And A means area meter square. Cos theta won't be having. Tesla meter square, or this Tesla meter square itself is known as Weber. Weber. It is represented by WB. If somebody asks you what is the unit of magnetic flux, you should be able to say Tesla meter square or Weber. Understood?
Yes.
Clear, no? Okay.
Yes.
Now the concept of magnetic flux is very, very clear in your mind, and you got a formula for this also. Now listen to me very carefully. This Faraday is there, no? I mean, there was a scientist called Michael Faraday. I mean, he did few experiments. Okay, Faraday's experiments, whatever NCRT has explained, I will come to them late at the later stage. Now, first of all, let me explain few things about Faraday's experiment. What he did. He did so many experiments. In that, first experiment is like, now what happened? Uh, I mean, he was passing this magnetic field like this. Okay, he was passing this magnetic field like this, and this magnetic field, whatever this magnetic field was there, no, it was changing. This magnetic field, what was happening? This magnetic field was changing. Now, in that, what happened? They placed one conductor here. They placed one conductor with some area. I mean, it is having some radius and all, and it is having some area and all. Okay, they placed it. And when this magnetic field was changing, no, they found out that, I mean, some current came into it. Some current came into it. Okay, some current came into it. Okay, so that is called as instead of current came into it, he used the word some current induced into it. Induced into it. Okay, just simply, I mean, he was placing this conductor, round conductor here. He was changing this magnetic field, and he saw that due to this changing magnetic field, some current came. I mean, direction of current and all we won't bother now. What is the direction of the current? The current started to flow in this whatever circular loop is there now, and this current started to flow. He was amazed. I mean, we haven't done anything. I mean, just by changing the magnetic field, the current is coming. And he did one more experiment. Like, I mean, that magnetic field was there. I mean, magnetic field was passing like this. Now, in this, what he did, he placed one more conductor. I mean, like this, he placed a conductor with radius r. Okay, now this time, let us take this magnetic field as constant. This magnetic field is constant. Now, but somehow this radius got changed. Somehow we don't know how. I mean, this radius, whatever this radius is there, no, this radius is changed. That means this circle must have become smaller one, or this circle must have become bigger one. Some things by one or the other method, this radius has changed. Radius has changed means area will change or not. If radius is changing, radius of the circle means area will change. Now, when this area change, now this B is constant. When area change, then also he saw some current is induced in it. Some current is induced in it. Induced in it. Some current came again. Okay, so he was again mesmerized by this. Now, what he did, he took this magnetic field. Okay, and he kept this magnetic field constant. So he kept this magnetic field constant, and he placed one conductor also. Inside this, he placed one conductor also. This was having some radius, and whatever this radius was there, no, that area, that is also constant. So both of them area was also constant. But what he did, he rotated this coil. By holding it at the here and here. He rotated this. Okay, this coil is rotated. After rotating, he saw again some current is induced in it. Some current came into it. Okay, some current is induced means coming. Okay, some current came into it, induced in it. Current is induced in it, induced in it. So now what is happening here, dear children? Now here is rotated means, don't you think this angle between area and magnetic field it is changing? This circular loop, no, continuously it is rotating means, if it is continuously rotating means this theta is changing or not? This theta will be changing area vector. What is theta? Theta means you have seen, right, already. What is this theta? This theta is the angle between B and A, right? So that's why. So magnetic field is like it is flowing from left to right. It is flowing in this direction. So whatever this direction is there here, magnetic field is flowing like this. There is no issue with that. Okay, and this circular loop is also there inside, and this is rotated means theta is changing continuously, so that's why this current is also coming into it. So by looking at this, he was thinking this current is coming, no? So the reason for this current is like three reasons he found out. So what are those three reasons? They're like, first, like, what is that? A changing magnetic field. Everything else is constant. Whatever this area is there, this area is also constant here. It is not at all changing there. So due to that changing magnetic field it came, and due to this changing area it came, due to this changing theta, changing angle it came. So that means the reason for this induced current is like B, A, and theta, right? Correct, no? Are you understanding my point? What I'm trying to say? So if this current is coming, so whatever this current is there, no, it is coming because of these three things, no, dear children? Change in these these three things, right?
Yes.
Correct or not? Change in these three things is causing a current to come. Now, what are these three things? If I write BA cos theta means, don't you think it is a magnetic flux only? That means somehow if you change magnetic flux is changing means somehow by one or the other method, magnetic flux is changing means what is coming here? Current is coming or not? Current is induced or not? Yes or no? Please tell me. Yes? Did you get this, what I
Yes.
said? Okay. So by using that, so he gave some laws. Those are only known as laws of Faraday's laws. We call them as Faraday's laws. Faraday's Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. So before getting into Faraday's laws of electromagnetic induction, what are the experiment explained in this NCRT? I'll explain you. Okay, look at this, dear children. There, see, did you get this module or not? So whatever three situation, this is the first situation, second situation, and third situation. Did you understand all these things? Here, B is changing. Here, A is changing. Here, theta is changing. Right, dear children?
Yes.
Yes, so if they are changing means, don't you think magnetic flux will be changing? Because due to change in the magnetic flux, we'll be getting that current. All right, fine now. So what are the experiments explained here? No, they have taken one coil like this, okay, and they have connected it to galvanometer. One coil is taken like this, and this is connected to galvanometer. Now, this magnet is there. There is one magnet like this. North pole and south pole magnet is there. Okay. Now, don't you think magnetic field lines will be going like this from north? Inside also they will be coming. I'm not denying that. North pole to south pole magnetic field lines will be coming. From north pole magnetic field lines will be going like this. Okay. Now, when you move this magnet towards the coil, okay, let me remove all these magnetic field lines so that it becomes easy for you to analyze. So this north pole to south pole, whatever this magnet is there, no. So if you move it towards this, how is the situation? through this magnetic field lines will enter, right? So magnetic field lines will increase in this coil, no? I mean, this is circular coil. I have shown it there. Otherwise, you can take a solenoid also. You can take a solenoid and you can connect it to a galvanometer, and you can I mean move this north pole and south pole magnet in this direction. When you move this, don't you feel magnetic field lines will enter into this? If magnetic field lines are increasing means, if magnetic field lines, I mean magnetic field lines are increasing means, magnetic field lines are increasing means, don't you think flux is changing? Flux is changing. I mean flux is increasing. Are you getting my point? Flux is changing or not? Tell me, dear children.
Yes.
It is changing or not? So it is changing means, so this galvanometer is there, no? So whatever this galvanometer is there, this galvanometer shown deflection. It's shown deflection, right? So it's shown deflection in one direction. Now after that, what they have done, I mean the same solenoid or same coil, you can take this or this, anything is fine. So I mean same solenoid, when it was connected with galvanometer, no? So this north pole to south pole, whatever this magnet is there, it was here. When they stopped it here, I mean, from this place, from far away place, I mean, it was here. Actually, it was here. They came to this place means magnetic field lines increased. Now, I mean, it is at a, it stayed here now. It stayed here means, I mean, it is at rest now. It is at rest. If it came to rest means they saw that this galvanometer shown zero deflection. It came to zero deflection, and it came to 0 point. That means what has happened now? Now here magnetic field lines are entering, but it got fixed now. Okay, it is not at all changing now because it has become fixed now. Magnetic field line. Okay, it is not at all changing now. It has become fixed. So now afterwards, solenoid is there, no? So this galvanometer. Now he took away this magnet, north pole to south pole. So whichever was near to this, no, he took away this. Then again he saw that galvanometer there was opposite deflection. In galvanometer there was a deflection, but it was opposite in direction. When it was coming towards this, when it was coming towards the coil, galvanometer shown deflection like this, and when it was going away, so galvanometer shown deflection like this, opposite deflection was shown. So that means that they came to, I mean, they as in Faraday came to a conclusion that changing magnetic field or changing magnetic flux, rather than saying changing magnetic field, changing magnetic flux produces, or changing magnetic flux induces current in a coil or a current in a conductor. Clear? Is it clear? Is this experiment clear? Is this experiment clear, dear children? See, look at this experiment, no? Here was the coil and here was the magnet, and when they brought it near to this, magnetic field lines passes through it, and afterwards, I mean, due to that, I mean, some current came into it, it shown deflection, okay? And when it was stopped here, I mean, there was no deflection, galvanometer came to zero deflection, but again, when it was taken back, galvanometer shown opposite deflection. That means here if they have brought and kept, it means what is happening here, magnetic field lines are entering, but these have become constant. No, we don't need constant magnetic field. We don't want a constant magnetic field. I mean constant magnetic field as in we don't want constant magnetic flux. We don't want constant magnetic flux for this current. Okay, we want variable magnetic flux. I mean, always this magnetic flux should be changing. Variable magnetic flux is there means we'll get the current. Is it clear? Is it clear whatever I have done? See, one more thing, one more experiment he did. So this is like first experiment. So which is explained in NCERT. This is the first experiment. Okay, moving of this magnet. So what you have to write here, whenever the magnet is moved towards the coil, magnetic flux is increased and current is induced. When it is kept at only one place, at rest, magnetic flux is constant. That's why galvanometer came to zero deflection. When the magnet is moved away from the coil, magnetic flux decreased. That's why current came, right? Somehow magnetic flux has to be increasing or magnetic flux has to be decreasing. Magnetic flux, whatever it is there, no, that should be variable. then only I will get the current. If magnetic flux is fixed means fixed magnetic flux is there. Fixed magnetic flux is there means I won't get any current. So due to this fixed magnetic flux, I won't be getting the current. Is it clear?
Yes, sir.
Is it clear? Now one more experiment he did. So let us see this. I mean, for example, here is one coil. Okay, here is one coil, and in this to this galvanometer is connected. Now here is another coil, and to this another coil. There is one battery and there is one key like this. Okay, you understand the battery and key, no? So this is the voltage. Some battery is connected, and here I have got key. Now what happens? I mean, side by side he has put it, no? Now when this key is pressed, current will pass through it or not? Tell me. When this key is pressed, current will pass through it. And if current is passing through it, it will produce magnetic field, no? It will produce magnetic field lines or not? Tell me. I mean, this will start to act like a magnet. Current carrying conductor acts like a magnet, I told you. It will start to produce magnetic field lines. These magnetic field lines will pass through it or not? These magnetic field lines will pass through this coil. That's why this galvanometer shown deflection in this direction. Now, continuously this key is pressed. Continuously current is flowing now. Now this magnetic flux has become constant. No, initially magnetic flux, whatever was there, magnetic flux increased. So once the magnetic flux has increased, means this galvanometer shown deflection. Now, when you kept on pressing means this key is on always. So this magnetic flux has become constant or not? If that magnetic flux has become constant means the galvanometer came to zero deflection. Here is zero. Okay, here the meter will be there. I mean, this scale is there, and here somewhere here. I mean, at the middle, here is the needle like this. Here is zero. Then afterwards, towards right and towards left, all the readings will be there. Now, when this magnetic flux has become constant, means again this galvanometer came to zero. Now, this key is turned off now. Turned off means it is removed. Then what will happen? Current will decrease. Current is decreasing means magnetic field will also reduce. So due to that magnetic field is reducing, magnetic flux will also reduce. Then he saw that galvanometer shown opposite deflection. That means whenever flux is constant, no, there is no current. Galvanometer showing zero. Either magnetic flux is increasing or magnetic flux is decreasing. Both are fine. Then I will get the current. Maybe in opposite direction. Here I have got it in the right direction deflection. Here I got left deflection. But magnetic flux is changing means will keep on getting this current. But if magnetic flux is constant means current will be zero. Is it clear?
Yes, sir.
Is this experiment, whatever experiment I have explained, is it clear? Okay, you can draw this diagram also. I mean, side by. See, first of all, you should get this concept. What is that concept? That EMF or that current is coming due to what? Due to changing magnetic flux. That idea should come to you. So, how to write this explanation? When the key is pressed, magnetic flux will increase. Due to that increasing magnetic flux, we get deflection in the galvanometer. Okay. Then afterwards, when the key is continuously it is on, the magnetic flux has become constant. So that's why galvanometer shows a zero deflection. When the key is turned off, magnetic field decreases and magnetic flux also decreases, and galvanometer show opposite deflection. By conducting this experiment, we get to know that constant magnetic flux do not produce current. Changing magnetic flux produces current. Okay. So again, I am telling you, changing magnetic flux is there. No, this will be producing current. Is it clear? Is it clear whatever I have explained?
Yes, sir.
Okay. Changing flux will produce current. Okay. So right now we have come to Faraday's laws of electromagnetic induction. So everybody can put the heading. What is that heading? Faraday's laws. Faraday's laws of electromagnetic induction. So what are Faraday's laws of electromagnetic induction? Let us see that. And if this coil is closed, no, for example, if this coil is closed, then only current will come into it. See, this is a closed path, no, that's why current will come into it. If this is not closed means current won't come. For example, here also all these circles and all we have taken, no, so these circles and all these are closed, right? So that's why we got current into it. Now, if these are not closed, for example, I have placed, this magnetic field here. Okay, this magnetic field here. Now there is a conductor like this which is not closed. Okay, if it is not closed means current won't come into it. Voltage will come. One end of this will convert into positive, another end will become negative. Now if you close it through a resistor, what will happen? At that time current will start to flow through it. Okay, whenever magnetic field is changing, no, so magnetic flux is changing, no. If the circuit is closed means current will come. Okay, now current is okay, but if it is open, now if it has become open means this current also won't be there. Voltage will be coming, and when I close this, I mean this voltage is called as EMF, no. So EMF will be induced, right? Did you understand this? Yes.
Yes, sir.
Look at this. This conductor is open means EMF will come here, but current won't come. Okay, fine. So keeping that aside, let's move forward. So Faraday's laws of electromagnetic induction. First law says whenever, write down this, I will explain one more time. Magnetic flux, whenever magnetic flux linked with a coil, changes. Changes means you understand, no? It may increase or it may decrease also. Whenever magnetic flux linked with a coil changes, an EMF, an EMF is induced in it, and current flows if the coil is closed. Okay, this is the first law. Whenever magnetic flux linked with a coil changes, I mean flux should be changing. It should be changing. It may be increasing or it may be decreasing. Both are possible. Okay. Whenever magnetic flux linked with a coil changes, an EMF is induced in it, and current flows through it. Current flows through it if coil is closed. If coil is closed. So this is the first law. And along with this first law, we write one more point here. EMF lasts as long as as long as there is a change in as long as there is a change in magnetic flux. Okay, this is very important point. The magnetic flux should keep on changing. So whatever this magnetic flux is there, no, that magnetic flux should keep on changing. Then only EMF will last. EMF will remain. Otherwise, it won't be remaining. So this is the complete first law of electromagnetic induction. Will you write this in the exam if it comes? It's
Yes,
quite simple, no, dear children? So whenever magnetic flux linked with a coil changes, increase or decrease, an EMF is induced in it and current flows through it if coil is closed. And EMF lasts as long as there is a change in magnetic flux. If change in magnetic flux is there means it will remain. Otherwise, it won't be remaining. This is first law. And second law, look at the second law. Second law is EMF, or you just say magnitude of EMF. Magnitude of EMF induced in a coil is directly proportional to rate of change of magnetic flux. Rate of change of magnetic flux. Rate of change of magnetic flux linked with the coil. Linked with the coil. So what do you mean by rate of change of magnetic flux? For example, here is the coil. Okay, I have got the coil here. So for example, if you are moving this magnet very quickly, then more EMF is produced. More EMF quickly if you are moving it. I mean very fast. I mean flux is changing very fast, right? I mean more quickly it will show deflection. Now, this coil is there. You have connected the galvanometer. But if you are moving this North Pole and South Pole magnet slowly, if you are moving, I mean less EMF is produced. I mean Here, what is there quickly means change in magnetic flux is more, no? Rate of change of magnetic flux is more or not? Yes or no? Rate of change of magnetic flux is more in the first case. So whatever this first case is there, no? There it is more. Here it is more quickly means it is more in nature, right? Slowly means, here it is less, no? So slowly means a rate of change of magnetic flux is there, no? So I mean that is less, correct? So that rate of change of magnetic flux is less means, so that rate of, please write down all of this. Rate of change of magnetic flux is less. That means less EMF. Clear, dear children? Is it clear whatever I have mentioned?
Yes.
So that's why I'll get
Yes,
less
sir.
EMF. I mean, while writing all these things, no need of this. Actually, there is no need of writing these diagrams and all, both of this, whatever I have written here. But I told you, so whatever this magnitude of the EMF is there, no? This magnitude of the EMF is directly proportional to rate of change means you understand, no? Delta pi b divided by delta t. Okay. So rate of change. So we also write it as E is directly proportional to d pi b divided by dt. Have you heard rate of change? We used to write, no, acceleration is equal to dv by dt and velocity is equal to ds by dt. Rate of change of velocity is called acceleration. We used to write all these things, no? So similarly here also, so this magnitude of the EMF is directly proportional to rate of change of magnetic flux. Okay. So actually, if you are writing delta means it becomes average. And if you're writing d pi b by dt means it becomes instantaneous. Okay. What is this average and instantaneous? We'll talk about this. Already you must have talked about this in the 11th class also. Differentiation means it is instantaneous, and a change, delta means change, right? So then it becomes average. I will come to that. All those things, whatever are there, I will explain them as the chapter proceeds. In this class, if you understood about Faraday's laws of electromagnetic induction means that is more than enough. Now, moving forward, this is understood, no? This formula understood or not, dear children?
Yes, sir.
Okay,
Yes, sir.
fine. And one more thing we write here. I mean, let's not worry about this E average and En. You can write them or you can leave them also. Generally, what we write here, no, you can write no issues. So this we write magnitude of this EMF is a, this is proportional to delta pi b divided by delta t. We write this much, and this magnitude is, to remove this proportional sign, we give n here. N means number of turns. How many number here? Only one turn is there. If more turns are there means, more EMF will be coming. So n, and we just write delta pi b divided by delta t, and we put one minus sign also. Here, there is a meaning for this minus sign. We mention it in Faraday's second law, and that is Lenz's law. I'll come to that. So here, n means what? N means number of turns. Number of turns in coil, and this negative sign comes due to Lenz's law. There is a law called Lenz's law. Lenz's law. What is this Lenz's law? We'll come to that later in the next class. Okay. This Lenz's law will be explained in the next class. Okay. So if they're asking about Faraday's laws of electromagnetic induction, first of all, you should be writing this statement. So this is compulsory. And second statement, you have to write no need of these diagrams and all. You should be writing this formula and carry it forward and this explanation. This much you are supposed to write. Understood, dear children?
Yes, sir.
Yes, sir. Yes.
So this is a 3-mark question, and this will come in your exam. Then you should be able to write these answers. I hope it is clear. Did you enjoy the class, dear children?
Yes, sir.
Yes,
Yes,
sir.
sir.
How was it? Was it informative and you understood everything? ಎಲ್ಲ ಅರ್ಥ ಆಯ್ತಲ್ಲ?
Yes, sir.
ಏನೂ ಬಿಟ್ಟಿಲ್ಲ ನಾವು ಇದರಲ್ಲಿ, ಎಲ್ಲಾನು ನೀಟಾಗಿ ಹೇಳ್ಕೊಟ್ಟಿದೀವಿ ಯಾವ ರೀತಿಯಾಗಿದೆ ಅಂತ ಹೇಳಿ. ಹೌದಾ?
Yes, sir.
ಓಕೆ, ಯಾವುದು ಬಿಟ್ಟಿಲ್ಲ. ಇನ್ನೂ ಬೇಗ ಬೇಗ ಮುಗಿಸ್ತಾ ಇದ್ ನಾನು, ಬಟ್ ಹೆಚ್ಚಿಗೆ ಅರ್ಥ ಆಗ್ಲಿ ಅಂತ ಹೇಳಿ ನಾನು ಬಂದಿರೋದು. ಓಕೆ, ಎಲ್ರು ಬರ್ಕೊಂಡ್ರಾ?
ಎಸ್
ಓಕೆ, ಕೊನೆಗೆ ವಿಡಿಯೋಲ್ ಬಂದ್ಬಿಡುತ್ತೆ ನೋಡಿ ಎಲ್ಲ ಸಮರೈಸ್ ಮಾಡೋದಕ್ಕೆ. ಸೊ ಇದೆಲ್ಲ ಫುಲ್ ಸಮರೈಸ್ ಆಗುತ್ತೆ. ಈ ನೋಟ್ಸ್ ಕೂಡ ಬರುತ್ತೆ ನಿಮಗೆ. ಓಕೆ, ಈ ನೋಟ್ಸ್ ಕೂಡ ಸೇವ್ ಮಾಡೋದಕ್ಕೆ ಇಟ್ಬಿಡ್ತೇನೆ ನಾನು. ಓಕೆ, ಸೊ ಈ ನೋಟ್ಸ್ ಸೇವ್ ಕೂಡ ಇಟ್ಟರು ಕೂಡ ನಿಮಗೆ ನೋಟ್ಸ್ ಕೂಡ ಸಿಗುತ್ತೆ ಎಲ್ಲ. ಓಕೆ, EMI 01 ಅಂತ ಮಾಡಿದ್ದೀನಿ. ಸೊ ಆಮೇಲೆ ಬರುತ್ತೆ. ಸೊ ಟೋಟಲ್ ಆಗಿ ನಿಮಗೆ ಫೀಲ್ ಬರೋದು ಭಾರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಇದರಲ್ಲಿ. ಓಕೆ, ಕಾನ್ಸೆಪ್ಟ್ ಅಂತೂ ಲೇಟ್ ಆಯ್ತಾ ನಿಧಾನಕ್ಕೆ ಆಯ್ತಾ, ದಟ್ಸ್ ಅ ಡಿಫ್ರೆಂಟ್ ಇಶ್ಯೂ. ನಾನು ಕಾಣಿಸ್ತಾ ಇದ್ದೇನೆ ಈಗ ಎಲ್ರಿಗೂ?
ಎಸ್ ಸರ್.
ಓಕೆ, ನಾನು ಹೇಳಿರೋದು ಇಷ್ಟೇ. ಇಲ್ಲಿ ಈ ರೀತಿಯ ಕೈ ಇದೆಯಾ, ಏರಿಯಾ ವೆಕ್ಟರ್ ಹೆಂಗಿದೆ ಇದರಲ್ಲಿ ಪಾಸ್ ಆಗಿ ಹಿಂಗೆ ಹೋಗ್ತಾ ಇದೆ. ಏರಿಯಾ ವೆಕ್ಟರ್ ಅಂತೂ ಈ ಕಡೆ ಹಿಂಗೆ ಹೋಗ್ತಾ ಇದೆ. ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿದ್ದಾನೆ. ಏರಿಯಾ ವೆಕ್ಟರ್ ಈ ರೀತಿಯಾಗಿ ಸರ್ಫೇಸ್ ಏನಿದೆ ಇದಕ್ಕೆ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಏರಿಯಾ ವೆಕ್ಟರ್ ಇರುತ್ತೆ. ಇದರಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಈ ರೀತಿಯಾಗಿ ಪಾಸ್ ಆಗಿ ಹೋಗ್ತಾ ಇದೆ ಅಂದ್ರೆ ಈ ರೀತಿಯ ಕೈ ಹಿಂಗ್ ತಗೋಬೇಕು. ಆಕ್ಚುಲಿ ಈ ರೀತಿಯ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಅಂತ ಗೊತ್ತಾಯ್ತಲ್ಲ. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಡೆಫಿನೇಷನ್ ಫುಲ್ ಕ್ಲಿಯರ್ ಆಗಿ ಗೊತ್ತಾಯ್ತು ಎಲ್ಲರಿಗೂ. ಏನದು? ನಂಬರ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಪಾಸಿಂಗ್ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಟು ದ ಸರ್ಫೇಸ್ ಈಸ್ ಕಾಲ್ಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ತಾನೆ. ಅದ್ರ ಯೂನಿಟ್ ಎಲ್ಲ ಗೊತ್ತಾಯ್ತು ನಿಮಗೆ. ಅದ್ರ ಯೂನಿಟ್ ಎಲ್ಲ ಅರ್ಥ ಆದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಏನ್ ನೋಡಿದ್ವಿ? ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಫಾರ್ಮುಲಾ πb = BA cos θ. ನೆನ್ಪಿಡ್ಬೇಕು ಅದನ್ನ. ಹೆಂಗೆ? πe = EA cos θ ಇತ್ತು ತಾನೆ. ಸೊ ಹಿಂಗ್ πb ಏನಾಗುತ್ತೆ? BA cos θ ಆಗುತ್ತೆ. ಓಕೆ, ಸೊ ದಟ್ಸ್ ಒನ್ ಥಿಂಗ್. ಅದಾದ್ಮೇಲೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಮಾಡಿದ್ವಿ, ಸಾಕಷ್ಟು ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್. ಒಟ್ನಲ್ಲಿ ಬಿ ಚೇಂಜ್ ಆಗ್ಲಿ, ಎ ಚೇಂಜ್ ಆಗ್ಲಿ, ಥೀಟಾ ಚೇಂಜ್ ಆಗ್ಲಿ, ಒಟ್ನಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಏನಾದ್ರು ಚೇಂಜ್ ಆಗ್ತಾ ಇದ್ರೆ ಏನ್ ಬರುತ್ತೆ? EMF ಬರುತ್ತೆ. ಇಂಡ್ಯೂಸ್ಡ್ EMF ಅಂತ ಕರೀತಾರೆ. ಒಂದ್ ವೇಳೆ ಸರ್ಕ್ಯೂಟ್ ಆ ಕಾಯಿಲ್ ಏನಾದ್ರು ಕ್ಲೋಸ್ ಆಗಿದ್ರೆ ಅದ್ರಲ್ಲಿ ಏನ್ ಪಾಸ್ ಆಗುತ್ತೆ? ಕರೆಂಟ್ ಪಾಸ್ ಆಗುತ್ತೆ. ಅದಕ್ಕೆ ಏನಂತ ಕರಿತೀವಿ? ಇಂಡ್ಯೂಸ್ಡ್ ಕರೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಆಮೇಲೆ ಸೆಕೆಂಡ್, ಅದು ಒಂದೇ ಲಾ. ಅದು ಏನದು? ವೆನ್ ಎವರ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಲಿಂಕ್ಡ್ ವಿತ್ ಎ ಕಾಯಿಲ್ ಚೇಂಜಸ್ and EMF is induced in it, and if the coil is closed, the current will flow through it. ಒಂದೇದು. ಆಮೇಲೆ ಅದ್ರ ಜೊತೆಗೆ ಇನ್ನೊಂದು ಪಾಯಿಂಟ್ ಏನ್ ಬರಿತೀವಿ ನಾವು? ದಿಸ್ EMF ರಿಮೇನ್ಸ್ ಆಸ್ ಲಾಂಗ್ ಆಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಇಸ್ ಚೇಂಜಿಂಗ್. This EMF lasts as long as magnetic flux is changing. This is first law. And second law, what is the second law? The magnitude of the induced EMF is directly proportional to rate of change of magnetic flux. ನೀವೇನಾದ್ರು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಕ್ವಿಕ್ ಆಗಿ ಚೇಂಜ್ ಮಾಡ್ತಾರೆ, ಹೆಂಗಾದ್ರು ಚೇಂಜ್ ಮಾಡಿ, ಫಾಸ್ಟ್ ಮೂವ್ಮೆಂಟ್ ಮಾಡಿ ಅಥವಾ ಇದನ್ನೇ ಆ ಕಡೆ ಮೂವ್ಮೆಂಟ್ ಮಾಡಿ, ಒಟ್ಟಿನಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಎಷ್ಟು ಕ್ವಿಕ್ ಆಗಿ ಚೇಂಜ್ ಆಗುತ್ತೆ, ನೀವು ಫುಲ್ ಸ್ಪೀಡ್ ಆಗಿ ರೊಟೇಟ್ ಮಾಡಿ. ಜನರೇಟರ್ ಎಲ್ಲ ಮಾಡ್ತೀವಲ್ಲ, ಸಿಕ್ಕಾಪಟ್ಟಿ ಸ್ಪೀಡ್ ಇಂದ ರೊಟೇಟ್ ಮಾಡ್ತೀವಿ. ಮಾಡೋದ್ರಿಂದ ಸಿಕ್ಕಾಪಟ್ಟಿ ಅಲ್ಲಿ EMF ಜನರೇಟ್ ಆಗುತ್ತೆ. ಹೌದಾ? ಸೊ ಇಟ್ ಈಸ್ ಡೈರೆಕ್ಟ್ಲಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ರೇಟ್ ಆಫ್ ಚೇಂಜ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್. ಸಿಕ್ಕಾಪಟ್ಟಿ ಚೇಂಜ್ ಮಾಡಿದ್ರೆ ಸಿಕ್ಕಾಪಟ್ಟಿ EMF ಬರುತ್ತೆ. ಸೊ E ಈಸ್ ಪ್ರಪೋರ್ಷನಲ್ ಟು D ಪೈ ಆರ್ ಡೆಲ್ಟಾ πb / ಡೆಲ್ಟಾ t. ಆಮೇಲೆ ಅದು ಪ್ರಪೋರ್ಷನಲ್ ಸೈನ್ ತೆಗೆಕ್ಕೆ N ಅಂತ ಇಟ್ವಿ. ಆಮೇಲೆ ಒಂದು -N. ಎಕ್ಸಾಮ್ ಬರೋದು ಇಷ್ಟೇ, ಬಟ್ ಅದ್ರ ಹಿಂದ್ಗಡೆ ಇರುವಂತ ಸ್ಟೋರಿ ಎಷ್ಟಿದೆ, ಆ ಸ್ಟೋರಿ ಗೊತ್ತಾಗ್ಬೇಕು ತಾನೆ. ಆ ಸ್ಟೋರಿ ಗೊತ್ತಾದ್ರೆ ಈ ಡೆಫಿನೇಷನ್ ಅನ್ನ ಬೈ ಹಾರ್ಟ್ ಮಾಡೋದು ಬರೋದಿಲ್ಲ ನೀವು. ಈ ಡೆಫಿನೇಷನ್ ಅರ್ಥ ಆಗಿರುತ್ತೆ, ಈ ಲಾಸ್ ಗೊತ್ತಾಗಿರುತ್ತೆ. ಹಿಂಗಿತ್ತಲ್ಲ ಅಂತ ನೆನಪು ಮಾಡ್ಕೊಂಡು ಬರೀತೀರ. ಸೊ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಬೇಕೋ ಬೇಡವಾ ನಿಮ್ಗೆ ಈ ರೀತಿಯಾಗಿ? ಹೇಳಿ. ಎಸ್, ಓಕೆ, ಫೈನ್. ಸೊ ದೋಸ್ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ಸ್ ಆರ್ ಮಸ್ಟ್. ಆ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಅಂದ್ರೆ ಬೇಕೇ ಬೇಕು. ಅದರಿಂದಾನೇ ಅದ್ರ ಹಿಂದ್ಗಡೆ ಇರೋದೆಲ್ಲ ಪ್ರೊಸೀಜರ್ ಗೊತ್ತಾಗುತ್ತೆ. ನಾನು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಾ ಇದೆಯಲ್ಲ ನಿಮ್ಗೆ? Okay, fine. So this was all about electromagnetic induction for today's class, and tomorrow I'll be talking about Lenz law. Lenz law ಬಗ್ಗೆ ಮಾತಾಡ್ತೀನಿ. ಮತ್ತೆ ಮುಂದ್ಗಡೆ ಏನೇನಿದೆ ಅದನ್ನ ಕ್ಯಾರಿ ಫಾರ್ವರ್ಡ್ ಮಾಡ್ತೀನಿ. Okay, all right. Thank you very much. Have a good day and bye bye.
Thank you, sir. Bye.
Bye, sir.
Bye everyone.
Bye,
Bye.
sir.
Thank you, sir.
Bye.
Bye, sir.
Bye everyone. Bye.